Okay, so the next thing that we're going to be doing is we are going to be looking at deriving the model to calculate the speed of growth and the acceleration of the growth. So here I stated what the best polynomial was for our model. Down here I've stated that I'm going to be taking the derivative of this function with respect to, that should be t because our variable is in terms of t. You could leave it as x if you wanted and then substitute. No, change it to t. Okay, so if I take the derivative of this linear function, I'm going to end up with, plus gets the equation editor, dy over dt will be equal to negative 4.30303. So the next thing that you'd want to do is make sure that you're putting this in terms of something that makes sense. Now, if you didn't choose to go with a linear function, you'd have another function here. So what we would be doing if we had another function is we're going to do it anyway. We're going to go to Excel and we're going to get it to fill out this table of values. So in this space here, I would have all my preliminary data. In this space here, I would enter in the new function that I want it to perform. So in this case, it's just going to be equal to negative 4.300, like that. And now I'm going to pull that data down like that. Now, if you ended up with your polynomial model, so let's go back and look at the polynomial. So that's not the assignment. If I chose the polynomial model, I'm just going to half screen this so I can have them both up, then the derivative of this polynomial model would have been 2 times the a value, t, plus whatever the b value is. So over here, in this space, I would have done, now I'll just show you to the side here, equals 2 lots of the a value that you see over here, minus 0.189394 t, or in this case, it's not going to be t, it's going to be times this value here, plus our b value of negative 1.84091. Okay, so that is the input that will give me the gradient or the speed of increase there. So if it was a polynomial model, then its rate of change at that point would be negative 1.84. So if I pull that down, you'll see all of those values will change based on what their gradient is at that point on the line. So this number here will represent the change in subscribers with respect to time. So every month we are going down by 1,000 subscribers. So that's what we found there. Okay, now the acceleration will tell us about the rate of decrease of this. So for this one, if I take the derivative of my linear function, I'll just get 0, enter, and then I would just drag that down. Okay, and like I was saying before, in this space here, I should have these values. So I'm just going to enter them in now. 5460, 5440, 5490, 5490, 5480, 5480, 5480, 5470, 5470, 5460, 5460, and 5480. Okay, so this is the table that I can put in at the end to say what I found. So when your acceleration is 0, that means that it is not increasing or decreasing in speed. Just means that it's staying at a constant rate. Okay, so just to be clear about what I would be expecting to see in this section of your solve part, I would expect for the speed of the growth, you show that you've taken the derivative of it, you've shown what that new function is, and then you've shown your table of values so that when we know that when we're at 0 months, this is the speed of the growth. So you should also be stating somewhere what this means, which is that in the first month, you would expect, now these should all be negative as well. The negatives just appeared above it. If I just move this across, you'll see that. So in the first month, you should be expecting to lose 4.3 thousand subscribers per month. Okay, and then you're going to do the same down here for your acceleration. So I've got the derivative of the function above, and I've shown that I've done that to get to this, which is just 0. And then I would state that this means that the acceleration is constant, meaning that it is not increasing or decreasing in the speed of its growth. It's just staying constant.